typo here.
Yeah, makes me nervous.
Yeah. That explanation of this thing was good. The set size is small and like the P is great in one case and D is big in one case. So what? So now we have to use this personalized low-as local lemma, right? Yeah. No, it's fine.
Just didn't work. Still have like 30% of battery. Shut down.
Okay, so today we're gonna finish how to compute approximate max flow in nonlinear time, and then we will, I will give you the overview of everything again. So just to recall, the problem that we wanna solve is here. Approximate max flow. So you are given a graph, and you're given the demand. You want to find the violating cut, or you want to find the flow with condition 1 plus epsilon that satisfy the demand. And we reduce this problem to something much simpler. Okay. So first step, we just say that instead of finding the flow that satisfies the demand exactly, you just want to find some feasible flow that just epsilon satisfy the demand. And by that, I mean the residual demand, right, is small. How small? It means that the total residual demand on every set S is small compared to the cut size. That's the problem. And how to solve this? Well, like it seems hard because there are like a 2 to the n set we need to check. But it turns out that we don't need to look at exponentially many cuts. There are just actually linearly many cuts that we need to look at. And that is because of what? Because of the existence of what?
Approximator.
Flow sparse.
Yeah, tree flow specifier that implies something that we call a congestion approximator. Good. So, yeah. So basically, we said that there is something that is called congestion approximator, which says that, okay, if you know that it's just a collection of cuts, such that if you know that the total demand on each cut in this family is small compared to the cut size, if the total demand is small compared to the cut size just for this thing in the family, then this is true for every cut, but with some like blow up factor of Q. Just because of this, like, and we show that it exists, this thing exists, given a tree flow specifier, and the quality is just, so we show that like this thing exists, the quality is polylog, and because this congestion approximator is defined from the tree. So the number of cuts that we need to look at is just 2n. And one can construct it in linear time too. So this is a bit better than what we actually show in class. In class, we show expanded hierarchy that implies slightly worse congestion approximator, but yeah, it's kind of almost the same. Okay, and because of this, we now reduce the problem to here. Just output either a cut, the violating cut, or a feasible flow such that the total residual demand on the cut of the congestion approximator is at most this. That's all we need. Okay, and how do we do that? We will use something that we call like a multiplicative weight update. Okay. So I will not recap this part. I will just try to recap it when we need it. Anyway, the multiplicative weight update is the framework that allows us to solve any LP by reducing it to something much simpler. And because of that, if we want to use multiplicative weight update to solve this problem, we would need to rewrite this thing in the form that is similar to LP. Okay. And actually, what I would do is that I would try to rewrite this thing in a way that is similar to LP, and we saw last time that if I just rewrite this thing as epsilon prime, and we define incident matrix B here, then you can convince like that this is true if and only if both of these inequality are true. Okay, and this is just like a some linear inequality, some linear constraint now. Okay, right? Like the variable is just f, and this is just some coefficient, and this is just like everything here is fixed, right? Yeah. So, okay. Good. Okay. So now, like this is just some number, some fixed number. And this is just some like a vector product, like some f with something here. Okay. So now we rewrite our goal to be just you either want to find a violating cut or you want to find a flow such that to say that the flow is feasible, you just write this thing. And again, this can be written as a linear constraint as well, right? Just two linear constraints. For this one, it's just two linear constraints here. So this looks like an LP now. You want to find f such that both of these, like all of these, are true. Okay. And when we try to apply the multiplicative weight update to find this such a flow, the framework require you to to specify which part you think of it as a hard constraint, which part you think of it as easy. So these two things will be hard constraint. This one is going to be easy. Right. Now I want to recap multiplicative weight update. So, think of you have any LP, you want to find x such that this is true. You think of this as hard. This is easy. What is nice about multiplicative weight update is that it allows you to basically just collapse all the hard constraints into one. That is, there will be rounds, and in each round, the framework will give you some like a vector that is a weight for each hard constraint, and then it basically do some weighted average of all these hard constraints into one, and you just need to solve this problem. What you need to solve is actually you want to find a feasible solution for this one, but with one more thing that you need. Not just any feasible solution for this, but you at least want it to be to have small width. That is the solution that you find. If you look back into the original constraint, it doesn't violate or over-certify any constraint by too much. Okay. If you can do this, and you're gonna do it, actually this is gonna be something like 2. Yeah. In our case, yeah. If you can do this, then it's and proceed to the next round and keep doing this for different PT. The framework says that if you have proceed in this way for this many round, something like log n rounds, then once you just average everything that you have solved on each round so far, this x bar, the average of your solution, is going to be very good solution. It's going to be almost satisfy all the hard constraints up to epsilon additive factor. And the easy constraint is satisfied anyway, because each of the xt is in this, is certified this. And we say that actually this set is a convex set. So the average is going to be in the convex set too. Okay, so that's the recap for multiplicative weight update.
Controlling just how fast this converges.
How fast it converges, it really just depends on rho here. Yeah. So if you have something like a very good oracle here where rho is small, it's going to be good. Otherwise, it just depends on rho square. Okay. So it means that in round T here, the framework will give you some weight. It will fix you some weight. What is the weight? It's basically do like for each of these hard constraints, there will be some weight associated with it. So the weight, I think of it as P here, and for each, like this is just for each set in the family, and I think of it like a plus hard constraint and negative, positive hard constraint and negative hard constraint, just because like they are just almost the same, right? Except that this is like negative here. So there will be like for every set in the family, and I just use plus and minus to distinguish two sets here. For each of these constraints, I get some number. Okay, some positive number. Okay. Is it clear? Like the framework just gives you some weight for each of the hard constraint. Okay. And what you need to do, you just look at this thing where you average, like just multiply, like for each of these constraints, you multiply with its corresponding weight, and then sum everything up. So what you get is just this like a scary looking equality, but it is not that scary actually. So let's try to like simplify it. Okay. Just try to write this thing. Like let's say that I write this thing. Okay. So note that this vector 1 here is just like an indicator vector live in R to the V, right? And each of these is just a number. The same thing here, right? So this is just some vector live in R to the V. Okay. And if I write this like, I just define this as like, I call it a potential, like because this vector live in R to the V. I think of phi V as a potential of V. This is just potential on each vertices. And now, once I define phi here, you can see that this whole thing just simplified to this thing, right? Like you can just factor f out here, and you get like actually you factor bf out, and you get like phi times bf. The same thing on the right hand side. Okay. So phi is just some positive, not positive, some vector live in R to the V. Okay. So this syntactically really simplify things, but let's try to understand a bit more about phi. What it means intuitively. Try to just interpret this a bit, right? So I claim that phi of V, the V entry of phi, can be written just in this way. Like you just really sum, like you just look at, you ask, what is the set that contains V? For each of those sets that contains V, you will like you sum this term up, right? It's really just like follow from this thing. Yeah. So look at all the set from the family that contains V, and then look at the weight of that set, the weight on the plus side and minus the weight on the minus side. And that's something and divided by the cut size. Okay. So that's like it has some intuitive meaning. Yeah. Okay. By the way, because actually you know that V is contained in not too many sets, because this family the family of congestion approximator is defined from the tree with log n depth, right? So each node is contained in just log n many sets. So because of that, you can compute the whole vector in n log n time. So it's fast to compute this phi. Make sense? So the way to think about this is just like you have your graph here. So maybe you have a set of node V here, and then there are like some family. Like the congestion approximator looks like this, right? It's just a laminar family of the whole vertex set. And each of this, for each of the set here, you have two numbers associated with it, the PS plus and PS minus. And if you want to compute phi of V here, you just kind of sum up all the set that contains it. Sum this thing up. Yeah. Anyway, you can compute phi fast. Yeah. And by the way, you can. This doesn't matter, but because this family is defined by a tree, actually you can say that you can compute it in actually linear time by doing some bottom-up thing. Anyway, doesn't matter that much. But now we can say that okay, in route T. Given the weight, you can compute the vertex potential phi, and all you need to do is to solve this thing. Like a phi is given to you like explicitly, and you want to solve this, right? Now, like okay, let me look at it. How do you solve this thing? Like it just have kind of two inequalities, this one and this one. Okay. I claim that it just suffices to find the flow that you know that it maximizes this term, as long as the easy constraint is satisfied, right? Because if you find ft that maximizes this, then you just check if this, like, after you maximize this term, is it still like at least the right hand side? If it is, then you're done in this round. And actually, this might not happen, right? It might be the case that this thing is strictly less than this. And if this is the case, then we cannot feed it into multiplicative with update framework. But I'm gonna claim that if phi, after you maximize it, right? If this thing is less than this part, then actually you can find the y-relating cut, and you're done too. So you either find a solution to the average problem, and you can fit it to multiplicative weight update, or you find a y-relating cut. Okay, that's our plan.
But because it's just like some average of constraints is violated, then there must be one constraint that's like violated.
Let's see. Let's see. That sounds right, but somehow I use some more complicated argument. Let me think. So idea is just saying that if like what we do here is just really we just look at this thing and we average everything together, and if even after averaging, then you say that this is infeasible, then there must exist some constraint that is infeasible too. So that sounds right to me. Yeah.
But I think that only give us that one of these things from the family, those cuts, we have to find a violating cut in the whole graph, right?
No, but if you get any violating cut, that's fine. Like,
But then the Q factor, I mean, does that create some trouble?
Let me think. Let me try to think about this offline. Yeah, but it seems correct what you said. Yeah. Okay. So now we reduce our problem even further. You have this problem, and you said that now you just want to find f such that this is true, and you maximize this term. How to solve that? Well, to do that, let's try to understand this thing a bit more, this term. We just expand the expression and try to understand what it means. Well, when you have this thing B, just by well, I claim that phi BF is just this thing, and this you can do it just really like by looking at how B is defined. Right? B is defined to be such that this is a matrix B, and B, and there is 1 minus 1 for each of the edge here, 1 minus 1, and so on. You multiply it with F of size edge, and but here it's like this is phi. This live in R to the V. So if you multiply phi with this is phi times B, each of this thing is just gonna be like, each of this term is just like multiplied this thing with this thing. So it's gonna be phi V minus phi U. Yeah. Right. So this is what it is. Okay. And how do you maximize this thing? You are free to choose f for every edge, such as long as f respect the capacity, right? So all you need so now it's clear. Like I will just set each of each of this term here to be the sign of this thing. If this thing is negative, then I make it negative, so that each of the thing here is positive. And once I set the sign, how much I should set it to is just the capacity of that edge, right? That's the, like, once I've maximized each of the term, like each of the term in the sum, I can maximize it, and that's the solution. So the solution is really like, for every edge UV, you look at which one has higher potential, and if V has higher potential, then you just send flow at full capacity from V to U. If U has higher, then just send flow at full capacity from U to V. That's how you set F in each round. Super simple, right? So now, and we can write down how large is this thing too. Like after you set F in this way, how large is this? It's just gonna be, for every edge UV, it's just gonna be the capacity of that edge times the absolute value of the difference between the potential. Make sense? How do you solve FT for each round? Compare the potential and send flow at full capacity along that edge, from higher to lower guy. Okay. So note again that, like, we are not really like look at like a ST flow with flow conservation and anything at all, right? We just want to find some vector that satisfies this LP. Okay. So now we solve the problem of finding F that maximizes this thing. And after you maximize this term, I'm gonna show soon that even if after you maximize this and it is still less than this thing, you're gonna get a violating cut and you would be done. I'm gonna prove at the last step. But if this thing is true, then it means that FT satisfy the average problem in round T. So you can feed it to the weight update framework and proceed to the next round.
Should we think of phi as the weights on the constraints?
No, phi is a number on each node.
Right.
So, like, the weight on each constraint is this P.
Oh, okay. I see.
Yeah. Like, on each constraint, you have, for each of the set, it corresponds to 2 constraints. You have 2 numbers for each of the set. But how to get phi, is from this equality. You sum up the P that contains it.
Okay.
Yeah. Okay. So that really completes the algorithm description, right? In each round, the framework somehow gives you the weight on each set, and you sum the weight on each set, and you get some number phi v for every node, and then you look at the graph and look at every edge. If the potential phi v is more than phi u, just send flow at full capacity from B to U. So that's your FT. And then okay, but you need to ask first, like, how many rounds there will be. Okay, And the number of rounds really just depends on the width of your FT. You remember that the number of rounds is just the width square log over epsilon square. So that is how much FT violate or over certify the original constraint. And I claim that the width is going to be just 2. Why is that the case? Well, let's look at the original constraint. The original constraint is just this thing, right? And this thing. So we want to prove that this term, like maybe call it A, minus this term B. We want to prove that A minus B is smaller than rho, and actually it's smaller than 2. We want to prove this. And note that, like, this thing minus this thing in the absolute value is the same A and B. Yeah. Right. So all I need to say is that this thing, this is like A, this is B. A minus B in absolute value is at most 2. Okay. And the way to do this is that I will just say that this term in absolute value, this term is at most 1, and this term is at most 1. If both of these are true, then I'm done. Okay, so let's do it one by one. Let's just look at this term. What is this? This is just really the total flow like this is at most. Yeah, actually this is like this thing. So this is just, you look at edges, like this thing is just to sum over all edges crossing S, right? And you look at the flow crossing this. But the flow is at most the capacity, because like at every time Ft respect the capacity. So it's at most the capacity. So this is just summing up overall capacity of a cut of S. So this is just the cut size. So this term is at most the cut size, but you divide it by cut size. So you get that this is at most 1. All right. And how about this term? Well, just look at this by definition. This thing is exactly the total demand on S, right? But actually, I can assume that the total demand on S is smaller than the cut size on S. Like, we can assume that this is at most the cut size for all S in the family. Why can we assume this?
We'll find a sparse.
Yeah, like if there are just n cut, you need to that escape from this family. And if this is not true, even from the beginning, we don't even need to check. You don't even need to do anything. Like, it gives you the violating cut already. So just from the beginning, you just check if this is true for every cut in the family first. If it's false, then you're done. So from now, we can assume that this is the case. So that means that this thing is at most 1 as well. So now you're done. That the width is most 2. So that it means what? It means that after like 2 times 2 square times log n times this thing, this I said instead of epsilon, I said epsilon prime. Yeah. After this many rounds, what you would get is what? What you would get is that if you just average all of your flow in every round, multiply it with update, guarantee that your flow is going to satisfy the constraint up to epsilon prime additive error, because you said epsilon prime here. And actually, I need another constraint too, that is like minus of this thing. This thing is true as well. Okay. But this is just what we want, right? It just implies that it just implies that f this thing implies that dfs is the most f in the family, and it means that f bar here, sorry. It means that f bar would epsilon satisfy d. Okay. So yeah, that's the algorithm. You have something like epsilon square, and know that, okay, I set d here to be epsilon, but epsilon is just epsilon prime here, but epsilon prime is just epsilon over q, but q is just polylog. So there are like epsilon 1 over epsilon square polylog many rounds, and in each round it's super simple. It's just linear time, right? Because in each round you first compute the phi first, and that takes like n log n, or actually even n. And to compute the flow ft, just look at every edge and compare the potential between the edge. So you see that the total running time is just linear times the number of rounds. Okay. So it's super simple algorithm, really. Like once you are given the cut approximator, then you just do something extremely simple in each round. Okay. And now I'm gonna say that, like, to complete everything, I need to show you that if this thing, the ft here, after maximizing this, like this thing, if it is less than phi times d, then you can get the violating cut. Let me present my proof. I will think about Aditya suggestion later. Okay, so note that ft is chosen in such a way that this thing is just this term, right? Recall, like, so I want to prove that if there exists phi such that the following is true, which happen if and only if this is the case, then we can find some cut, and actually it's going to be some threshold cut, s tau, where it's just all the nodes such that the potential is less than tau. Actually, more than at least tau, but it's the same thing here. this is the case, and this is like one of the threshold cut is going to be a violating cut. That's the claim. And how to do that? I will just start by note that in the beginning everyone has its potential, and I'm gonna just think of this as an embedding of node into real line, just like we have seen many times. And the first node is going to be phi 1, phi 2, phi 3, and so on, up to phi n. The first thing I'm going to do is I'm going to translate, shift the whole thing here so that this is at 0. And I claim that we can do this. And the reason is that, well, just look at the two terms here, right? This thing is translation invariant. You can shift everything, nothing change. But how about this thing? It's gonna change to this term times this thing, right? Every guy is shifted by minus phi 1. So, but d of v is 0. So it doesn't it stays the same again. So I now assume that phi 1 is 0. I can assume also that phi n is 1, because once I set phi, I can scale everything by some factor. Just multiply both sides by some constant. Nothing changed. Okay. So now it's really the node. There are the first node here, the end node here, and this is just between 0 and 1. Okay. There are many other nodes around here. And if you look at the, let's say now I choose a random threshold uniformly in this interval from 0 to 1. Okay, call it tau. And look at this, and look at this cut. Every guy that is greater than tau. Then let's try to analyze this. Well, let's look at the cut size of the expected cut size of S tau. It's gonna be just summing over all edge, right? And just its capacity times the probability that that edge is cut. But that edge is cut with this probability. This edge is cut only if tau is between phi u and phi v. Yeah. But this probability is just the absolute value of the difference between the potential. So this thing is just exactly the first term here. And how about the expected demand, total demand of S tau? Well, it's just for every node V, you look at its demand, and this is, now you know that phi of V is exactly the probability that V is in S tau. Right? So this is again this, the right hand side of the inequality. So because you know that this thing is less than this, now you see that this thing is in expectation, the cut size of S tau is less than the total demand of S tau in expectation. If this is true, then there must exist tau such that Like there must exist some tau such that this is the case. So yeah, and this is just a violating cut. Okay. So to conclude, you get like this running time. The linear, each round there are like linear time, and there are this many round. This is just the number of round. And you either get a violin cut, or you get the flow that satisfy this, and which imply that this flow, like this is like basically F bar. This flow epsilon certify D. Okay. So that completes the algorithm question about this. Do you think it's simple, or this is not simple? Okay, so actually in the tomorrow discussion, we're gonna analyze this algorithm, the same algorithm here, but on expander, and you will get even more intuition about it. It's gonna be something that is like supernatural. Like the algorithm is gonna be something like, suppose that you have S and T as a source and sink, only like just two source and sink. The algorithm is gonna be something like, each of the time you try to send the flow locally, like, just try to flood the flow to your neighbor, something like that. Gonna be some intuitive diffusion process. Try to send flow from S to T. And the reason is what it's so simple is because, first of all, the condition approximator for expander is just something very simple. It's just singletons, right? And we can try to analyze how things go like more precisely, like have some physical understanding of this thing. Anyway, I just want to stress a bit that what you have seen is quite remarkable. Like the history and the state of the art of MaxFlow problem, like it's just one of the cornerstone problem in the field of theoretical TCS, theoretical computer science, has been studied since the 60s. And you may have seen Ford Fulkerson and something else. But the point is that people have tried to look at it, and people get stuck at something like m to the 1.5 from the 70. And even in the unit capacity case, if it is like a general case, then it is quite slow. But in ATs, people can get MN either by blocking flow or push relabel that we have seen in class. And but then in 90s, then only then people can manage to get m to the 1.5 for general graph. But m to the 1.5 is just there from the 70 if you just look at unit capacity graph. So yeah, and then until like 2010, there was some breakthrough. And the idea is to use multiplicative weight update together with some primitive that is called electrical flow or Laplacian solver. And they managed to break this thing down to m into the 1/3. So at least 1.5 is broken. But it's not like as good, like as it's not perfect yet. And this is just still like a 1+ epsilon approximation. But yeah, after that, it turns out that the right object to look at is not elliptical flow. It's conjecture approximator as we saw. Just multiply, like use this thing together with multiplicative with update. Then you get what you saw. By the way, although this is remarkable, like super exciting, by that time, basically this thing, like these two papers, is shown almost simultaneously. This get the best paper at SODA, and this is stock or something, not sure. By the way, this is for edge capacitated graph, and it doesn't work for vertex capacitated graph. And the reason is that actually you cannot have conjecture approximator when it is about vertex capacitated graph. So imagine that your graph is a star, maybe. So this is maybe exercise for tomorrow. No conjecture approximator for a star when we talk about when it is about vertex capacity. Like we can prove that conjecture approximator just doesn't exist. So we just need something that is very different approach. And it turns out that just like this year, we can do it using something else. But again, it uses multiplicative weight update, and together with some dynamic graph algorithm. Yeah. So it looks like for approximation, things are kind of done. But in the exact case, a lot of things is still like going on, and it is very active area. And the hope is that maybe like in 5 or 10 years you can do it. Yeah. Okay. So let me give you some summary of the class. So the class basically has 2 parts, and the first part is more about structure of expander, and we have seen like basically 5 ways to look at expander, like the 5 equivalent ways. The first thing is about robust against deletion of the graph, and that is if a graph is a phi expander, it undergo actually not just deletion. In class they talk about deletion, but also actually insertions. Then you can find some set with small volume such that after delete this set of node, then the remaining is still a phi expander. Not just connected, but a phi expander. Okay. This is basically expander pruning. Also, in the cut, view, we saw that basically expander is the most well-connected graph among all graphs that have the same degree profile. That is, if G is a file expander and you have that this thing have less or equal degree profile, then G is going to be, the cut size of G is going to be more than cut size of H up to some factor. And you have seen like a flow too, that is actually cut and flow are basically the same up to log n, and it means that the graph, the expander is also like the most well-connected graph for flow view as among all graphs that have degree profile, like among all graphs that have the same degree profile. Okay, we have seen the eigenvalue view or spectral view, and this is via Shiga. Also random walk. So you can ask about like basically the mixing time of. Do you recall mixing time? What is mixing time? It's like the time that you start from any node and you do a random walk and you ask like about the distribution of like where you land, and if the distribution is like close to stationary distribution, then you ask how many steps you take before the distribution is close to stationary distribution, and that is called mixing time. And mixing time is just closely related up to log factor to the second eigenvalue. It's just the inverse of that. Okay. So you should like in the exam you should like at least see like why all this is true. Yeah. I will not ask you about like in this side of the proof why that is true, but like you should have intuitive understanding of all this.
Why is the exam?
Oh, the exam it should be 16 to 17. I will put some doodle for you to book the time. Yeah. Maybe some Excel's, some spreadsheet you can book the time. So that's the first part. For the second part, like not just structural thing that you have seen, it's also algorithm toolkit or concepts. There are a lot of things that you have seen. Metric embedding, power method, isolating cut, local cut matching game, balance cut. These things. So these are like a lot of things that actually everything is almost connected. And now I'm gonna like write down some diagram that maybe is a very important diagram for this class, but it takes the whole class so that you understand this diagram. So let's start. So let me start with the balance sparse cut. Okay. So most balance sparse cut. Yeah. Do you recall the problem? Can someone try to say what it is? Like, roughly.
You want a sparse cut, but you also want both sides to be kind of near the total set of vertices, so near n by 2 or something.
Yeah. So it need not be like super balanced. It should be as balanced as the most balanced one. Yeah. And given this one, you can use it to get an expander decomposition. Okay. Yeah. And if you remember, like we kind of have some recursive way to do it, like try to keep finding the balance cut. And we do some trick about changing the parameter. If you remember, like when even the most balanced one is not so balanced, then you change the parameter a bit and make it work, make it work somehow. Okay, but what we show in class is about like with the notion of expander that I showed the proof is about the expansion. But this strategy just works for any notion of sparsity, really. For if it is about conductance, just need to find the most balanced sparse cut where sparsity is conductance. Or it can be like general demand sparsity, where the sparsity is with respect to general demand. Can try to find the most balance with respect to this one. It will give you the corresponding expanded decomposition. And you have seen that you can even strengthen expanded decomposition a bit to be boundary linked as well. Okay. So I show how to get boundary link decomposition, and I just show the existence, and that's kind of enough, because once you can show the existence, then you can get slightly worse one if you use approximation algorithm, and so you can try to convince yourself at least that you can, like from here, if you have like linear time algorithm for this one, you can get linear time algorithm for this one too. Okay. And then from here, we can get three flow spacifier. And to do that, it's basically just expander hierarchy. Right. Just do boundary link expanded decomposition, and contract, and do it again and again. Get three flow specifier. This is like a nice specifier. But we also see a lot of other specifier actually in class. What is that? For example, we see that we can get good approximation cut specifier. This is edge specifier, right? You give it a graph. You want to find a graph that has linear number of edges, like O tilde n edges, but you preserve a cut. And how to do that is something like repeated X decom. So you do that, you get just a bunch of expander, and you know how to specify expander easily. Just kind of look at for each edge, you look at the mean degree between the two ends and sample according to that. It's very simple to specify expander, so you can get specification of the whole graph, because specifier are composable. there are other, for example, exact min cut specifier. Okay. So, okay. Anyway, so this is like, this thing is like, yeah, maybe do it later. Anyway, there are more, and maybe I listed more, but there are more specifier that I didn't present in this class that is based on expanded decomposition. But let's continue here. From tree flow specifier, you can get congestion approximator. And from here, we just saw today that we get approximate net flow. And to do that is like multiplicative with update. Okay. Let's look a bit from here. How to get balanced fast cut? Okay. Can someone say anything about how to get balanced fast cut? Just some keyword, maybe. Cut matching game. Yeah. And in the cut matching game, there will be two players, a cut player and a matching player. Okay. So, by the way, in this reduction here that I draw, it's really about like reduction between linear time algorithm. Right? So if you have linear time here, you get linear time algorithm here and so on. So what we want is basically fast cut player and fast matching player. And if you have both of them, you can combine them using cut matching game. And actually, cut matching game can be viewed as some version of multiplicative weight update too. And I didn't talk about this at all. I gave you some ad hoc analysis how cut matching game work. I just present it as a way to construct a expander from when you have a cut player and matching player, and how to get an expander from both player. And I give you the proof, but actually it can be put into matrix version of multiplicative weight update. Actually, this thing is something that I don't know exactly yet too, but some expert told me that it is the case, and it's not in the literature. I would like to understand this too, but anyway. So, but how do you get matching player fast? This is a new homework too.
Use approximate match.
Yeah. Now you kind of complete the cycle. So, as long as this is the H capacity version. So as long as the notion of sparsity that you want to work with is about H capacity. It can be this notion, like generic demand, but it is about edge cut. Then you can use approximate max flow with edge capacity. But if it is if it is about a vertex capacity, then no, right? Because this is about like this is max flow with edge capacity. But good with sparsity, which like with edge related notion of sparsity. Okay. But okay, this is like a chicken and egg now. But we actually saw that we can implement cut matching game fast in different way. Like do it from scratch using push relabel. Okay. And using ball growing argument, we can say that using by push relabel, you can either find a flow or you find a sparse cut where this sparsity is low conductance. Like push relabel is not good for any like notion of sparsity, but it's fast, it's good enough when it is about low conductance cut. Low conductance. Okay. And but from push relabel, we actually saw that it's good for many things, right? So you can get slow exact max flow as well. You can get many other things like local sparse cut, or expanded pruning. So it's like a technique that is very flexible and good for like even in a local setting, in the dynamic setting, and so on. Okay. How do you get fast cut player? We actually saw two algorithms for cut player in lecture. One is randomized, one is deterministic. And the randomized one is actually fast, right? So you can try to recall, but you can get fast cut player from something that you use, like something that has the same flavor as power method. You do some random projection and you do some threshold cut. So it's similar in spirit to power method. Just in spirit. But like they are based on like a computing like look at the spectral how like look at eigenvalue and so on, something like that. But you also see that the power method itself by Shiger, like when you want to find Shiger cut, you can use it to get some sparse cut too, like sparse cut.
Approximate.
Is it approximate sparse
Yeah, approximate sparse cut.
using feelers?
Yeah, it's called feeler cut. Yeah, but so this is basically from Shiger in the proof of Shiger inequality. So it's not balanced sparse cut, but it's sparse cut. So it's not like strong enough to get everything here, but at least it's something that seems useful. Okay. So this is randomized. Do you recall deterministic algorithm for sparse for cut player? What does it need?
Random walks?
No. So the deterministic algorithm for the cut player, it just call balanced sparse cut, right? If you remember, like you just look at the graph so far, find the balanced sparse cut. That's your cut, and you repeat it for log n times, and then you get the final cut. Like once you don't have any balanced sparse cut, you know that it's going to be the final round, and you proceed some way. But basically, you just need balanced sparse cut. So this is another cycle. Okay. And let's see more. So this is like, okay. How do I? This is gonna be something that, like, local thing, and this is gonna be something like about sparse cut thing. And this part is like a sparsifier thing. And this part is like flow thing. And there are other things that we look at too. It's like minimum cut, min cut. Okay. So I'm out of time, but I will just continue. So to get min cut, first of all, like this thing can give you ST min cut for sure, right? But there are other stuff. For example, we have seen local cut algorithm. It gives you like vertex min cut, or even like a directed. It works in directed graph too. We have seen other tools